Hello and welcome. We're about to dive into a little mystery that you've probably noticed every single day, but maybe never stopped to really think about. You know when a voice from another room sounds different? It's not just that it's quieter, the actual quality of the sound totally changes. We're going to find out why. So picture this. You're at home, maybe in the kitchen, and someone calls out to you from the living room. Their voice isn't just turned down, is it? It sounds muffled, kind of indistinct, almost like all the sharp edges of the sound have been sanded off. So what is actually happening to that sound as it travels from them, through walls and around corners, to get to you? Let's follow it on its secret journey. All right, so here's our game plan. We are going to trace the path of a single sound wave and see how its environment completely transforms it. We're going to look at 4 key things: how it fades with distance, what happens when it bounces off surfaces, how it gets absorbed by different materials, and maybe the coolest part, how it actually bends around obstacles. By the time we're done, you'll know exactly why that voice from the other room sounds the way it does. So here's the absolute key idea to hold on to. The sound that you hear is almost never the exact same sound that was made at the source. The environment itself, the room, the furniture, the air, it acts like a filter, changing the sound waves as they travel. You can almost think of the room itself as an instrument, shaping the sound before it ever reaches your ears. Okay, first up, let's talk about the most basic change that happens to any sound. It fades with distance. We all have an intuitive sense for this, right? Things get quieter the farther away they are. But the physics behind it is actually pretty elegant, and it has a name: the inverse square law. The inverse square law is one of those fundamental rules of physics that pops up everywhere. So what it says is that as sound radiates out from a source, its energy gets spread over a bigger and bigger area. Think about a tiny speaker in the middle of a balloon. As you blow up the balloon, that initial bit of sound energy gets stretched thinner and thinner over a much larger surface. The energy isn't lost, not at all. It's just diluted. So what does this mean in the real world for you and me? Well, here's a really simple rule of thumb. Every time you double your distance from a sound source, the sound level drops by about 6 decibels. And a decibel is just how we measure sound intensity. So if you're standing 10 feet from a speaker and you back up to 20 feet, the sound will be noticeably quieter. That rapid drop-off is the very first challenge for our traveling sound wave. Okay, so our sound wave is already getting weaker as it travels. But now it's about to face a new challenge: a wall. I mean, in the real world, sound hardly ever gets a straight, uninterrupted path. When it hits something, it has to kind of make a choice. Does it bounce off, pass through, or get absorbed? Let's start with the bounce. So why does sound bounce off a wall? It really all comes down to something called impedance. That's just a fancy word for how much a material resists being moved. Air, for example, has super low impedance. It's easy to move around. A solid brick wall, on the other hand, has incredibly high impedance. It's really, really hard to move. So when a sound wave traveling through easygoing air hits that stubborn brick wall, it's like a tiny ripple hitting a massive concrete dam. The wall barely budges, so most of that sound energy has nowhere else to go but right back where it came from. And you know what's cool? This creates a really neat illusion in our brains. When a sound bounces off a wall, our ears and brain interpret it as if it's coming from a point behind the wall. It's the exact same principle as your reflection in a mirror. It looks like there's another you on the other side of the glass. Our brain gets tricked into thinking there's a sound image back there. Now, let's take that idea and put it inside a room. The sound isn't just bouncing off one wall. Oh no, it's bouncing off all of them: the floor, the ceiling, every surface, creating this chaotic storm of reflections. So you hear the direct sound from the source first, and then, milliseconds later, you're hit with this dense barrage of echoes from every direction. This complex, beautiful wash of sound is what we call reverberation, and it's what defines the unique acoustic character of any space. And this is exactly why you sound like a rock star when you're singing in the shower. All those hard reflective tiles in a bathroom create a ton of reverberation. That dense cloud of echoes blends with your voice, it smooths out any little imperfections, and it just adds this rich, full quality to your singing. It's like having your own personal, invisible backup choir. The exact same principle is at work in a grand, resonant cathedral. Okay, so we've established that a lot of sound bounces off of surfaces. But what about the energy that doesn't bounce back? It can't just vanish, right? It has to go somewhere. And this brings us to the other 2 possibilities: absorption and transmission. Right, so when a sound wave hits a material, some of its energy gets absorbed. It's actually converted into a tiny, tiny amount of heat. You can think of it like the sound wave is getting tired out from all the friction of pushing its way through the material's fibers. Now, the rest of the energy, the part that's not reflected or absorbed, might get transmitted. This means it actually makes the wall or the door vibrate, and those vibrations create a new, weaker sound wave on the other side. And that is the key to our initial mystery. That muffled voice from the next room is the sound that has been transmitted through the wall. And here's where it gets really interesting. Different materials are good at absorbing different frequencies. Soft, fluffy, porous things like curtains, carpets, and acoustic foam, they are fantastic at soaking up high-frequency sounds. But low-frequency sounds, like the deep rumble of bass from a stereo, they are much, much harder to stop. They have these long, powerful wavelengths that can just power right through most common building materials. And that's exactly why you can often hear the thump, thump, thump of your neighbor's party, even when you can't hear the rest of the music. So we've talked about what happens when sound hits a surface head-on. But what if it doesn't? What if it just goes around it? This brings us to our final fantastic phenomenon, diffraction. This is sound's ability to bend around corners, and it's the last piece of the puzzle we need to solve our mystery. You've definitely seen this in action, even if you didn't know the name for it. If you've ever watched water waves in a pond bend and spread out as they go around a rock, that's diffraction. Sound waves do the exact same thing. When a sound wave passes the edge of an obstacle like a doorway, it bends around it, spreading out into the area behind it. It's the reason you can still hear someone talking, even if they're around a corner and completely out of sight. And here it is, the big aha moment, the solution to our mystery. How much a sound wave bends depends entirely on its wavelength. Low-frequency sounds have long, lazy wavelengths, which means they can bend around obstacles like doorways really easily. High-frequency sounds, on the other hand, have short, choppy wavelengths. They tend to travel in much straighter lines and get blocked by obstacles. So when someone's talking in the next room, the low, bassy parts of their voice bend around the door frame and into your room, but the high-frequency, crisp parts, the parts that give speech its clarity, get blocked. And that's why their voice sounds so muffled. This whole effect creates something called a sound shadow. And get this is a mind-blowing little fact. Your own head creates a sound shadow. It's true. If a high-pitched sound, like a bell, comes from your right side, your head will physically block some of that sound from reaching your left ear. And your brain uses that tiny, tiny difference in sound level and timing between your two ears to figure out exactly where that sound is coming from. It's this incredibly precise system that we use constantly without even thinking about it. So there you have it. Let's pull it all together. The 4 key ways that sound is completely transformed on its journey from the source to you, the listener. It's fading, it's bouncing, it's being absorbed, and it's bending. These 4 interactions are happening all the time, all around us, constantly shaping the auditory world that we experience. The journey of sound is just this fascinating story of physics and perception. It's the reason a world-class concert hall can sound so magnificent. It's why you can pick out a friend's voice in a super noisy room. It's a journey that's happening with every single sound you hear, and now you know the secrets behind how it all works. So that's our deep dive into the secret life of sound. The next time you hear that muffled voice from another room, you'll know exactly why it sounds the way it does. And hopefully, you'll listen to the world around you with a brand new sense of wonder. Thanks for joining me.